All right, so let's get started. So first of all, let's go through to QA. Last time, I think it's quite interesting. The first is, I already answered it. In Linux, it is possible to interrupt a user process even it is running kernel functions. And after the user process running kernel functions are switched back to the CPU, then they can resume from the kernel function they are executing. So it is possible to do it. And the second one is about the interrupt priority. So actually there are some amount of questions there about if interrupts can be interrupted by other high priority one. And the short answer is yes. And the technique is called nested interrupts. So nested interrupts allow one interrupt to preempt another if necessary. But I mean, it depends on different operating system. For Linux, it is possible to interrupt a low priority interrupts with a high priority. But for some, maybe like some real-time kernel, something like that, if they don't want to do this kind of complex management, then they will not allow nested interrupts. Okay, so that is about some interesting QA we have next time. Today we will focus more on the memory management part, but before that, let me quickly go through the the interrupt parts. Okay, so first of all, how CPU works with slower hardware device, we say there are two ways, pulling and interrupt. So usually interrupt is to let the hardware to signal the kernel, and pulling on the other hand, periodically, kernel will check the hardware status. There are two ways to cause interrupts. The first is, usually people call it power interrupts, and it works like an asynchronous way. Our device physically produce electronic signals. So your CPU will receive the signals and will be interrupted by the interrupt controller. And we show you this is the motherboard, and in traditional systems, there are north bridge and south bridge on the chips on the motherboard. And then north bridge usually we will plug with the DRAM and GPU load balancer device. South bridge on the other hand will be connected with keyboard, hard disk drive, PCIe, SSD, those kind of slower device. So south bridge usually is so like the IO for the IO function. So usually there is a thing called interrupt controller in the south bridge. It's going to notify the CPU, hey, actually we receive a signal from keyboard, hard disk drive, or some storage device. And after 2019, actually, for Intel CPU, they integrate the north bridge into their CPU. So currently, the memory controller, they are usually in the CPU. So there is no north bridge now in your motherboard. In addition to in addition to hardware interrupts, there are another category is called software interrupts, and that is the things you already learned last time. It's called system call part. So the exceptions are produced by the processor itself. So for example, when you run in a system call, it is more like your CPU already know you get a instruction is you are going to run the system call, right? So CPU will your CPU will interrupt itself. Or there's something like when CPU is doing the patch table walking, and when CPU finds like there is the data is not in the main memory, then for example, if it is in a store device, then there is a thing called patch fault, right? So patch fault in this case is CPU check the patch table and then it finds the data is not in the memory, so CPU will once again interrupt itself to handle the patch fault. So those kind of stuff like CPU will interrupt itself is usually called exceptions. So how an interrupt works. So how a device send out interrupt signals? So in this example, if keyboard is connected to the interrupt controller by IRQ1, then the IRQ1 will first be translated to the which interrupt numbers. So interrupt controller will do this translations by checking the interrupt vector table. So after translating IRQ1 to interrupt vector number 0x81, interrupt controller will send this 0x81 to the CPU's interrupt controller. So we call it the local APIC. So interrupt vector number 0x81 now is sent to the CPU. So the next step is, okay, we get this interrupt signal, but how to handle this interrupt? So the next step is how to get the kernel function to handle this specific interrupt number 81. Before getting the main function, we need to know where is the starting point for the function, right? Because usually there are a lot. For example, in this case, there are 256 kernel functions to handle each of the interrupt. So to know like where is the number 81 kernel functions, we need to check this static vectors table. So the static vectors table actually for each vector, it is a 4-byte size. And the reason for 4-byte is because each vector, it only stores a code segment and an instruction pointer. So the code segment and the instruction pointer combined together, you can know where is the target instruction. So code segment plus instruction pointer now usually is 4-byte. So this ISR 0 vector is 4-byte and this is 4-byte. So all of them, they are 4 bytes. So if we are going to know where is the number 81, we just need to do the multiplication. 81 times 4, so we get like 324. So CPU will directly read out the data from this memory address 0x324. So after CPU read out, actually CPU will get the code segment and instruction pointer points to the started address of the interrupt handler. So this code segment instruction pointer, CPU run it, and CPU will know, oh, actually, your starting point for ISR 81 is here. So CPU can fetch the instructions one by one from this address. Then CPU can run this interrupt, the 81's interrupt service routine or interrupt handler. So in this case, we can finish the handling interrupts part. I think next time we stop at this figure, right? So we forgot to mention one thing is actually interrupt service routine or interrupt vector. It is the function the kernel runs in response to a specific interrupt. So you can think about just like when you are doing your system code, then your system code function, you can also look like it is very similar to the interrupt service routine. So they are very similar because system code interrupts. One system code is a software way to implement the interrupt. So they are very similar stuff. So when you are writing your homework, actually, you can link them together. They are very similar idea. And in Linux, actually, the interrupt service routine, they are all part of the device driver. Okay, so there are the kernel code manage the device. And the challenge for interrupt service routine is usually, especially in Linux, they are non-blockable. So for the key term non-blockable is it cannot be stopped, it cannot be slid. So usually interrupt service routine cannot be preempted, usually. But in Linux, actually, as we already mentioned in QA, because in Linux it allows the nested interrupts. So even ISR is not blockable, but if there are some ISR being higher priority, it is still possible to preempt the current low priority ISR. But for the ISR with the same priority, they cannot be interrupted And also for some other, kernel functions, they cannot preempt the running ISR. Okay. So because ISR is non-blockable, so if each interrupt service routine runs a longer time than expected, then other kernel functions or your user process cannot get enough CPU to run, right? So the handler should run quickly to resume execution of the interrupted code as soon as possible. Okay. Oh, sorry. The interrupted code, just like for example, your user process or some other kernel functions. Okay. Those kernel functions and user process, they need the help from interrupt service routine, and they are called interrupted code. Okay. So the solution for this interrupt service routine is to split it into top halves and bottom halves. So top halves, you can think about it runs immediately upon receipt of the interrupt and performs only the work that is time critical. So on the other hand, bottom halves are those works that can be deferred, they can be delayed, they are not that so important, but they are not that time critical, so they can be executed when the system is doing the light loaded, when the system is like not serving the very urgent functions. Okay. So, sorry. Okay. So here comes an example. So if there is a network card receive a packet, then it triggers the network device interrupt, right? And here just come an example. Just like if your CPU now is handling a timer interrupt. So timer interrupt can be handled periodically because usually timer, like CPU will check the timer periodically. So timer interrupt usually is a low priority interrupt. But the network device interrupt usually is a higher priority interrupt, because if the CPU doesn't respond to the network device interrupt, then the network card will be blocked. So the network card cannot get new packet from the network. So there's overflow there. So the network device interrupt can directly preempt the timer interrupt to let the CPU first serve the network device interrupt. Okay, so this is the thing I say, this is a nested interrupt part for Linux. Okay. While CPU is handling the network device interrupt, there's there are two parts. The first is about called the top halves. So top halves acknowledge the interrupt and performs quick actions. So including reading the NIC chip status, the network card status, and making the buffer as ready. So they are doing a lot of like a status checking, and then to make sure your data is correct. So they are all done in top halves. But the data moving part, what I mean the data movement is to move the data from the network card buffer to the like host memory or kernel memory. They will be run during the bottom halves. So after finish the top halves, the interrupt service routine will be stopped, and then will be switched back to for example, the user process. And when there are some free time, or when system is doing the light loading, the kernel will activate the bottom halves, when it will keep running the rest of the paths, just like keep copying the data from the buffer to the host memory. So in this case, this network device interrupt can be served super fast, as it only needs to finish the top halves. And for the bottom halves, it doesn't really need to be finished at the moment CPU receive the network device interrupt. They can be split, and then they can be delayed, can be deferred. So this is the concept behind the top halves and bottom halves. Okay, so this is all about the interrupts. So next, we'll move on to another topic, the memory management. Okay, so for the memory management, we will split into two I would say like lectures. The first is about the physical memory management. So we will talk about the basic concept between the patch and patch frames. So patch is for the virtual memory management and patch frame is for physical memory management. And then for the physical memory management, because the physical memory, there are shared between your Linux kernel and also your user process. And in ancient time, because when people are using 32-bit CPU, actually the maximum addressing space is 4 GB because you only have the 32 bits. So you can only addressing 4 GB of the memory area. So in that time, they need a lot of complex management from kernel. So we will first talk about how to manage kernel physical memory. And then after that, we will quickly talk about there are several memory allocation. And first bit, best bit, worst bit, I believe you already know that before. So we will focus more on the body system and step allocator, which are very famous design in Linux. And after that, we will talk about the virtual memory management. So virtual memory management is what the user process can see and how you programmer know about the memory layout. So we will talk about the virtual memory area, including the heap, the stack, or the code sections. Like all the programmers can know those kind of area. So how those areas be linked to for example, to link to the DRAM and how to manage them. And then we will talk about the patch table. So we have virtual memory. So how to link the virtual memory back to physical. That is, we are using the patch table to do the translation. But patch table, actually, it takes a lot of time to do the translation. If each time we need to run the operating system to do the translation. So in modern Linux systems, actually, especially for x86 CPU, we'll talk about how to let the CPU work the patch table automatically without the help from operating systems. Okay. So first of all, and I think this we already talked about it in lecture 0, but I think this is very important, so I put it here again. So patch frame and like patch. Patch frame is the partition physical address space to chunks with the same size. And patch is the virtual address partition. And they are both aligned with the 4 kilobyte size. So patch frame is 4 kilobyte and patch is also 4 kilobyte. But patch frame, what we are inferring is about the DRAM part, just like how for each DRAM address, this is about the patch frame. For the patch, it's the virtual stuff. So it doesn't really directly map to the physical DRAM. Okay. So physical address is the location where the data actually stored on the DRAM. So this is the patch frame. And then virtual address is the location where the programmers think the data as. Okay. So assuming there is a CPU and here the rectangle means the DRAM, or we call it the physical address space. So we will partition this DRAM to a lot of 4 kilobyte patch frames. So they are all the same size, 4 kilobyte, 4 kilobyte, 4 kilobyte. So each of them, we call it a patch frame. And for all these kind of physical memory, you can think about there are two different privilege. So part of it, they are for kernel. So we call it a kernel address space. And the rest of it, they are for the user. So we call it a user address space. And the thing is, if we are going to access the patch frame belonging to the kernel address space, CPU needs the kernel privilege. So we say the CPU has a things called kernel mode. And when CPU is going to access patch frame in the user address space, then CPU is in a user mode. Okay. So given an example, if there is a process called P1, so P1 is for example, it's a C code, and this C code calls a things called memory allocation function. So you usually use it to allocate the dynamic memory in C library, right? So after calling this function, the kernel allocates patch frames to this process for this user process. So let's say if this is the patch frame allocated to the user process, Okay, then in the kernel address area, there's a thing called patch table. So patch table will record about, actually the virtual address returned to the P1 will be mapped to this physical address. Okay, so here is a VA. And each translation, we only need an entry. So each entry usually is like 32 bits or 64 bits. So it depends on different CPU architectures. Okay, so we will talk about it in more details in the patch table working part. Okay, so kernel manage all patch frames and maintain patch tables. So there are two issues: how to manage each patch frame and how to do allocations. So in this example, we just randomly pick this one as our patch frame, right? But the problem is if we are going to get a larger one, or if we are going to get a smaller one. What I mean smaller one is because, come to think about, if you have a kernel data structure that only need like 40 bytes, then this smaller size, should we also allocate a 4 kilobyte patch frame for this to store this 40 byte data? And actually in the kernel, there are a lot of data structure that are smaller than 4 kilobytes, because 4 kilobytes is quite larger. For example, we talk about the text structure, right? Text structure is for the process control block. They are going to describe the process. And in addition to text structure, there are also like file system. There are also like networking. There are also like the interrupt, those kind of descriptor. So those kind of descriptor, they are not really huge, as large as like the 4 kilobyte. Usually it is smaller than 4 kilobyte. So how to manage those kind of, I would say, like tiny data structures on those kind of frame. Okay, so that is for the kernel part. But for the user part, virtual memory management, that all processes share the same physical address space via patch tables. So each process has their own patch table, because when you are doing the programming, actually you don't know other programmers how they doing the memory layout, and you don't really need to know, because for each programmer you always get a new 4 kilobyte or even 4 gigabyte or even larger virtual memory, and it always start from, for example, 0 to 4 gigabyte. So you don't know how others use this 4 gigabyte. And the reason you can do those things like this easier and portable is operating system helps to manage all these kind of dirty works. So a very quick example for patch table working is actually inside your CPU, there are two different, I would say, like components. One is called a TOB, another is called MMU. So TOB works like a patch table entry cache. So we will do the patch table translations to do the VA to PA translation by the MMU, memory management unit. And after doing the translation, we will store the result in the TOB. So TOB just like a cache. So next time, if there's another request and it belongs to the same virtual address, we don't really need to do the MMU translation again. We can directly get an entry result, the physical address from the TOB. Okay, so given any, and in modern systems, actually, all of the instructions in your code, it will be first in the virtual address. So what CPU first see always will be virtual address. Usually CPU will not get the physical address directly. So you can think about, once the system starts to execute it, your C code or any other code, actually what CPU see is their own virtual address. So address translation happens very frequently, because for each instruction it needs to do the translation from virtual address to physical address. So it takes a lot of time for doing this kind of translation stuff. So TOB is very important. If there is no TOB, your system performance will drop a lot because every time you need to do the page table walking. Okay, and actually page table walking, it takes sometimes, and I will show you, I think next week, because it is a little bit complex task. So if if this virtual address is not in the TOB, CPU will, MMU inside the CPU will walk the page table. Okay. So page table walking is just like what one will do. And then after getting the physical address, your CPU can use this physical address to get the data from the page frame. Okay. So that is the virtual address, virtual memory management part. And we will talk about that next week. So first of all, how to manage each page frame. Okay, so before answering this question, we need to first answer another question. So why we're using 4 kilobyte, like page and page frame? And we know for processors, like if you are using the CPU, if you are familiar with the CPU cache, actually for the cache line is like 64 bytes. Actually, it is in the byte level, but byte page is in the like kilobyte level. And the reason is actually for your modern processors now, their smallest addressable unit is a byte. So it is possible for your CPU to get only byte. Just like getting a word is like 2 bytes. But the reason, like in the memory, we are going to manage in this kind of page size is because the overhead. So come to think about it, if each time, I mean, you are going to get the data, and the data like is in the byte level, so your maintenance table will be super large, because even there is a 4 kilobyte area, if you are going to maintain this 4 kilobyte area in a byte level, then you need 4 times 1024. That is, let's say 4096. This amount of the management overhead. Because if you're using a 4 kilobyte, then actually you only need one data structure to maintain the 4 kilobyte area. So the granularity for doing the management plays a very important role in operating system. So this is the reason why people are choosing 4 kilobyte. But actually, currently in some scenario, for example, cloud computing or like some virtual machine scenario, it is possible for operating system to support to 8 kilobyte page size. Because for those scenarios, actually getting a larger page size getting more benefit. Okay, so page size is a adjustable like unit. You can also say you are going to align with the CPU cache, so you're going to change your page size to 64 byte. Theoretically, it is possible, but it is not workable on Intel CPU, because the page size is not only about like you're going to partition your memory to what kind of page size. It is also about how to manage your cache table. Because next week we will show you actually if we are going to do like 4 kilobyte or like 2 megabyte page, it is possible to directly reuse the current page table architectures. So you don't really need to change too much of your operating system and CPU. But for example, if you are going to say you are going to use like 5 kilobyte or 3 kilobyte, or why not using like 2 kilobyte or 1 kilobyte, then you need to redesign your operating system a lot. And also your CPU probably need to do a lot of adjustment on those kind of register management stuff. Okay, so 4 kilobyte. Okay, so how to manage this kind of 4 kilobyte area? So there are several counters or fields that are required. So to manage those related, also like metadata, we need a thing is called the descriptor. We need a structure page. This is you can think about this is the page frame descriptor. So page frame descriptor, it looks like this kind of stuff. Okay, so for each page frame, you will get each of this kind of page frame descriptor. Okay, so this structure, the first field is about the flag. So the flag indicates it is a dirty or it is locked or this is a clean. So those kind of status, we can use this flag to reflect about each of the status of each patch frame, and then count how many reference. Because actually for each patch frame physical area, they can be shared between a lot of process. Like you already learned it when you are using the copy on write, right? When you are going to copy on write, you are going to create a new process by using copy on write. At the very beginning, a lot of information they are shared between your parents, including a patch frame. So at that time, one patch frame can be shared between your parents and your child. So there is a counter here. This counter is going to indicate how many references there are. Okay. So if the patch is used by the patch cache, because patch cache is more like when you have a storage device and you are going to read the data from a storage device. But usually storage device is super slow compared with the memory, right? So for example, you are going to read out the document, and maybe a couple minutes later, you are going to read out the document again. But you don't want to read your document from a storage device again, right? Because it is super slow. So you will cache, you will store your document in the DRAM. And the area to store your data from the storage device is called the patch cache. Okay. So how to differentiate the patch frame? It is for user process like heap, or it is for stack, or it is for the patch cache. Actually, the patch frame here using the address space to make this differentiate. Okay. And also there is a things called index part. Index is because now you know there's a things called swap. Like if you don't have enough main memory, then you are going to put part of your data to the storage device. Then you will enable things called swap. So swap is about you can swap your process data to the storage device. But the thing is, if the data is not, if the required data is not in the DRAM now, then actually you will use this index to find out where is the data on a storage device. Okay. So this is for a swap file. And then we also need a thing called the patch replacement, right? So when we are going to do the patch replacement, actually we run the LRU. But how to choose about which patch frame should be evicted, which patch frame should be used? So there is a thing called like LRU list, but this LRU is not the LRU you learn typically. This is the Linux-based LRU. So there is a slight difference between them. And then the last thing is about the virtual address, because this is a physical patch frame. So we are going to usually it can be reimbursed back to link where is the virtual address pointed to this patch frame. Okay. So actually we say for each patch frame we need each of this patch frame descriptor or this structure page data structure, right? And people were asked about overhead, because actually if we have like 4 GB of the DRAM, then 4 GB divided by the 4 KB, then you need 1 million of this kind of structure page area, right? So 1 million actually, it sounds like it is a very huge overhead, but actually for each structure page, it doesn't really take too much of size, because each structure page you only get 40 bytes. So even 4 GB DRAM, it requires only 40 megabytes for these data structures. So it is an acceptable overhead. Okay, so after talking about the patch frame, like there are a lot of patch frame now. If you are using a 4 GB of the DRAM, then you have million of the patch frames need to be maintained. But how Linux maintain those kind of patch frames? So for example, how Linux know which part is for kernel, which part is for a user. Actually, Linux is using a things called zones. The kernel uses zone to group patches of similar properties. Okay, and primarily there are 3 kinds of zones. One is called zone-DMA, and the second is called zone-normal, and the third is called the zone-high memory. So if you look at descriptions, zone-DMA is for DMA-able pages. So the reason why we have this zone DMA region in the kernel memory, and actually it is not large, usually it is more than 16 megabytes. The reason is, in ancient time, when we are using a DMA, you need to first know where is the physical address to copy the data. So this zone DMA is going to meet this requirement. Actually, this is the physical address segment for the driver. So DMA driver always know where is the usable memory to put this kind of DMA data. Okay. So you can think about this zone DMA area, they will be first allocated there, and then all of the DMA data movement, they will be moved to this area. Okay. And after DMA, there is a very large portion, it's called zone normal. And normal is just like normally addressable pages. So most of the pages, most of the page frames, they are belonging to this area. Okay, and the next one is called zone-high memory. So high memory is quite tricky. The reason is Linux, actually, it is designed from the very ancient time. What I mean ancient time is because at that time, your CPU is only 32 bits or even fewer bits, usually 32 bits at that time. But when you are using the 32-bit systems, actually, you can only address to maximum like 4 gigabyte of the memory, right? But for the 4 gigabyte memory, we say kernel can only use the 1 gigabyte area, and the rest of the 3 gigabyte they should be kept for the user process. So 1 gigabyte actually sometimes it will be not enough to manage the kernel data structures, because kernel there's also can do the dynamic memory allocation, those kind of stuff. So to handle this possibility to use more than 1 gigabyte, in ancient time there's a thing called zone-high memory. So for zone-high memory, it is a dynamic mapped area for the kernel. Like with using this dynamically mapped pages, it is possible to use more than 1 gigabyte. And this part is a little bit tricky, so I put it at a very less of this lecture. Okay, we will first talk about the zone normal and zone DMA part. So zone normal is the zone contain normal regularly mapped pages. So DMA is for page frame that can undergo DMA. And then this one is page frames are not permanently mapped into the kernel address space. Okay. So not only the zones, because zone is not enough. Come to think about our computer architectures now. Like there is a thing called the UMA, Uniform Memory Access. Let's say you have 2 CPU, and these 2 CPU, they share the same memory controller. So memory controller can connect to the DRAM, right? So in this case, no matter which CPU access which DRAM, the latency is the same. Okay, so this memory controller you can think about as before 2019. Like before 2019, actually there is node bridge. So node bridge helps to handle those CPU and DRAM communication. But after 2019, Intel integrated the memory controller into the CPU. So after that time, actually each CPU can directly connect to the DRAM. So you can see these structures. Like in most of the server and then workstations, if you have 2 CPU now, they're using this kind of non-uniform memory access pattern, like the NUMA pattern. So NUMA, the reason we say NUMA is because when CPU on the left-hand side access the DRAM on the left-hand side, we call it the local access, because the path is shorter and the latency is also shorter. But when the CPU when the CPU on the left-hand side is going to access the DRAM on the right-hand side, we call it the remote access. And usually the time is 2 times the local access. Okay, because this CPU should talk to this CPU first. So after talking to this CPU, DRAM data can be moved to this CPU and then moved to this CPU. So the latency is quite a lot. And the reason like we cannot directly move the data from this DRAM to this CPU is there is no connecting wire between this CPU and this DRAM. Okay, so the wire is here. So we need to move the data from here to here and then to here. Okay, so if you have a server, then you can open your server. You can find actually if you have two sockets, like you have two CPU, like you can find actually most of the DRAM they are connected very close to the CPU, and there's like this kind of structures. Okay, so NUMA is widely used now, and due to this reason, Linux also needs to support NUMA. Okay, oh, why NUMA? So first of all, because you can get a fast local access, actually. So if you are using these structures, actually, memory controller will become a bottleneck, because if you have a lot of requests, then memory controller will be overflow. And there is a contention issue here, so memory controller should handle a lot of stuff. And the thing is, if the loading is too high for memory controller, sometimes it will crash. Then there is a single point of failure. So there are a lot of issues for this kind of centralized, I would say like this kind of centralized architectures, or like this UMA architecture. And also for the architecture on the right-hand side, the system can get a higher bandwidth. So because for each memory controller, it can only support limited amount of the DRAM. So each DRAM you can think about maybe it can serve for 64 GB. So if the memory controller can only serve for like, let's say like, for example, 10 DRAM, then the overall bandwidth can be 640 GB, right? But for this architecture, this one can support 10 DRAM, and this one can support 10 DRAM. So overall, we can support like 20 DRAMs here. So theoretically, you can get the higher bandwidth, but I mean, this is theoretically. Yeah. So the third one is easy to scale up, and the reason is because the left-hand side you always need a central point here. So it is really hard for you to scale to a larger capacity. Okay. So if you are going to insert more CPU in the right-hand side architecture, then you can support larger memory capacity. Okay, so this is why in most of the server, if they need higher bandwidth, if they need to support higher memory capacity, then they need to choose for NUMA. Okay, so for NUMA, actually for each DRAM and CPU pair, we will say it is a memory node. Okay, so actually in Linux patch frame management architectures, like it looks like this. So it allocates memory from the node closest to the running CPU, because this is quite important, right? So if now your process is here, like you always hope your data is in this DRAM, so you can always enjoy the local access. But if now your user process is running on this CPU, but your data is on this DRAM, then probably you need to take like 2 times of the time. So do the correct allocation is very important for this memory allocation stuff. So if you look at the granularity part, actually we will first check about the nodes and check the zones and check the frames. So when we are doing the allocation, we will first check about the nodes, just like if the request and the data is in the same nodes. So this is the node zones, and then this is a node, and then below the nodes there is 3 different zones. So this is for DMA zone, normal zone, and high memory zone. And below this zone there is a patch frames. So this is the hierarchy between nodes, zones, and patch frames. Okay. So that's the concept of memory allocations. So initially, all memory is available theoretically, and is considered as a large block of whole, right? So when a process needs memory, the system searches the set of the whole that is large enough for this process request. So there are three very basic memory allocation way. The first is called first fit. So first fit is search and allocate the first hole that is big enough. Okay. So the drawback for this first bit is it size, because it is possible the first bit is a super large hole, but your first memory request only needs 4 kilobytes. So you allocate this super large hole to it, then you waste a lot of memory size. Okay, so here comes another, it's called batch fit. So batch fit is the kernel search all the holes and allocate the smallest hole, which is big enough. Okay, and the problem is it takes a lot of time because you need to search to all the holes and then to check the size. And here comes the worst case. Sorry, not the worst case. Worst fit. So worst fit is search all holes and allocate the largest hole. Then it wastes size and time. And maybe you have one question is why we need worst fit. So worst fit is this is the worst decision at this moment. But maybe in the future, if the memory demand for the certain process grows, then it maybe can fill the largest hole. Okay, so it's just for now, this is worst case, but maybe in the future, if this process keeps needing more memory, then the process doesn't really need to do the memory allocation super frequent. So worst fit for some scenario, actually, in the long term, in the global view, it is not the worst case. Okay. So we will talk about fragmentation because like actually you do the allocation and you do the deallocation. So there will be some fragmentation that cannot be used by the process because the size is not fitted the request from the user process. So there are two fragmentation. The first is called external fragmentation. So external fragmentation is enough total memory space to satisfy the request, but the available space are not contiguous. So like this, actually you have process 1 and process 2 data, and here is the total amount of memory you have. And the white part is those available memory. And now you have process 3 to reclaim like you need this amount of memory. And actually the white part can, the aggregation of the white part can fit this P3's demand. But because now the data is, the space is split from two area, it's not contiguous. So this is called external fragmentation. And paging can solve this stuff because paging is to partition the whole memory space to the same size. So if it is in the same size, then actually it is possible to, for example, if you are going to get a contiguous area, you can just move P2 to here and you have a contiguous space because you have the same size. So you can move all the data all around the memory if you want. And there comes a thing called internal fragmentation. So it occurs when system splits the contiguous space into contiguous chunks. So this is for if you are using a paging, then the thing is how large your page size is. So at the very beginning, we say your CPU can do the byte addressable. So it is possible for each memory you are going to maintain in a byte granularity. Then in this case, probably there is no internal fragmentation because you manage in a byte granularity. But the problem is you will take a lot of overhead, including the space overhead, the performance, the time overhead to manage all those huge amount of the metadata. So people try to increase the size of the page size. So now you have a decision of 1 byte, but you say actually this is not a good decision. So you increase to 4 kilobyte, right? But the thing is 4 kilobyte for user process, it is a good decision because user process usually your image or like maybe your data structure usually can be larger than 4 kilobyte. But for kernel, this is not the case because for kernel is the things that you can run beforehand, right? Before running your user process, you will launch your kernel. So kernel is a static stuff. And before you run a kernel, you already know like your text structure, how large it is. And for example, you already know your patch frame structures, how large it is, because those are all code. So you already know, hey, your heterogeneous structures is only 40 bytes, right? But if you are going to put this 40 bytes things in 4 kilobyte area, then it will waste a lot of the space because 4 kilobyte means the 4096 byte, right? 4096 bytes is way more than 40 byte. It's around around 100 times larger than this area. Okay, so this is called internal fragmentation. Let's say you always partition into the 4 kilobyte, but you cannot really use all the you cannot fill all the 4 kilobyte for all the requests. Okay, so let's stop here and take a 10.
就是我们做 system call 的话，到底是只说我们只做的那个 system call，就是只做那个 handler，还是只说 system call 只是把 CPU 的 mode 转到 kernel mode 这件事？
你实现那个才是system call，
才是 system call 吗？
对 ，CPU 转 mode 只是 CPU mode switch 而已，因为 CPU 转 mode 不一定是 system call 造成的。
因为我去查说，他就说这个流程是那个什么，就是那个 glib 给那个 library 给我们那个嘛，然后它里面的 wrapper 会转成，就是它里面的 wrapper 会把我们的那个给我们的那个 API 转成那什么，就它里面会做的事情会就准备好参数，然后会 return 一个 system call，所以这其实就会转到kernel mode，然后只是 handler 才会去查那个 table 嘛，然后得到我们注册的那个
system call number，
得到我们注册的那个 system call 函数。
对，
所以我们真的写的那个才叫 system call。
我觉得应该要
都很多，就有人叫 system call 第一期是，就是你在那个 wrapper 帮你转换成，然后把它转成 kernel mode 的那个叫 system call。
但我觉得定义，我个人觉得很重要，因为基本上就是这整个流程都是算 system call 的环节。
这个流程。但
是你如果真的要说你从你的 kernel programmer 可以做的 programming 的话，那就是去定义了你 system call 要做什么事情。那件事情就是你那个function。那其他的事情是什么去驱动这个function做的事情？
其实不用管太多这种。
我是觉得定义没有都非常重要。对，做到这个程度的话，对。对。
好，了解，这样是。对，我想就是期中考试下礼拜，那考试是可以是只写英文，还是可以中英夹杂？就是比如那种讲一般都中文，但是最后也是用英文，这样可以吗？
可以，对，
这样子。
这边为什么？对，我要传给他们，就是不能直接传给他们。对。
你说这个吗？这个是传这个 ISR 第81个它那个function的第一个 instruction 过去给 你从这边拿嘛，因为你不同的 ISR 你大小会差很多，那你没办法去确定说就是每一个 size 是多少，因为这个就是 ISR 有大有小，所以如果你要去把它像这样做的话，那你要记录说第一个 ISR 的起点是哪里，第二个 ISR 起点是哪里，第三个 ISR 起点是哪里，所以它会需要花额外成本就是这件事。那比较简单的做法就是我直接把它存在这边的资料里面，那 CPU 就可以 CPU 就有就是比较动态的做法可以去做到。对，就是你要直接拿也是可以，只是这样的话，你 CPU 就要去用更多 register 去记说那谁在什么地方这样子，所以它这样子是其实是把它的成本转嫁给记忆体。对，
那个问题就是所以它的用是干嘛用？为什么还要是？
哦，
对
弄的原因是因为这个就是 Linux 它的概念是从0.1版开始一直延伸到现在，所以它会有很多东西是在例如1点多版、2点多版那时候设计的，但是因为它为了要上下兼容，所以它会一直延到现在。那这种概念是在那个年代，像如果要做 DMA 的话，那时候的系统它会需要预留一个固定的实体机体位置下来，就是一开始你在做那个 booting 的时候，你就要先预留一个实体机体下来，空间下来，然后你的 DMA 的控制器知道说那个位置要怎么去做对应，DMA 才帮你办。所以这块是刚才说那个 ROM DMA 所负责的，但是现在系统不用，因为现在本来就是 DMA 都很聪明，所以你随便丢那个机体位置，它都可以办，所以这个就变得没有那么会用到。那这边其实虽然说有3个，但其实大部分的空间都是丢给第2个，也就是一般正常 kernel function 会用到的那个空间。
就是我的意思就是它这个用它是干嘛用的？就是不太懂，他是要把就是上面写相同特性的东西连在一起，然后这样才比较好去
比较好去管理。就是例如你今天有个 request 来了，那你这个 request 是一个 normal 的 kernel function 的话，你就可以直接分配这种 normal 这个区域的 page frame 就好了。因为有可能性是，假设你今天是个 DMA request，所以你这个 DMA request 你就不能拿这种 normal 的 page frame 区域啊。所以你就会需要去拿这种 DMA 底下的空的这些 page frame 来做使用。对，
那这句话是什么意思？就是
这个比较难理解，因为它这个点是在当初在设计 Linux 的时候，因为它是32B 的系统，32B 系统你只能用最多4GB 的空间，然后在那时候 kernel 只能用1GB，3GB 要给 user，就我们一开始讲那个情境，但1GB 对于 kernel 来讲，有些时候它用不够。那用不够的话，它怎么办？所以它特别预留了一个100多 MB 的空间，是可以去存取到其他的 page frame 的位置的。对，可是它就可以动态定址，它就没有要固定定址在那个地方。对，所以这是个很特殊用途。这个，如果我今天有时间可能讲到，如果没有的话，可能就下次一开始会讲到这个用途怎么用。对，
但是我也永远都会是它是可以一直，
因为 kernel 的 address space 基本上是永远都会，就是它的 virtual 到 physical 的 address 的转换其实是一个固定的一个转换，就是它基本上它的 page table 只做一个加 OK 的动作而已。对，所以这边讲的永久的意思，其实就在讲的是它除了这个 high memory 区域之外，其他的区域其实都是1对1的对应关系。就你这个page frame 其实不好意思，你这个 virtual address 其实对应到这个 page frame，对，它不会像 user 一样是随机对应的。
所以像这个它就是可以一直变，
它跟 user 比较像，它需要透过 page table 去转。对。
然后那个 PPT 第13页，
第13页，
这就是如果说这 CPU 如果是3个、4个的话，是要怎么连？
就一样啊。
如果
就是
这个
应该没有3个 CPU，因为通常是4个，4个就是这个复制出来，然后这个 CPU 是这样传，
所以中间也是要连。
DRAM 一定只能跟某一个 CPU socket 连在一起，
对，所以就是
中间就是会它串成一个
OK
方框这样子，然后你可以让 CPU 这左上方传资料给 看他要不要交叉，反正就是看你的线要怎么拉这样子。
所以那个是
对
设计师自己设计的。
对，你就是如果通常都会交叉，因为这样你要传的距离比较快。对。
那我想问那个就是每个 process 它有个每个 process 都有一个 page table，
对，
然后每个 page table 就有很多 page entry，
对，
那每个 entry 它不是都指向同个 page table 那个同个 process 东西，
对，
所以说它的每个 entry 资讯量都不一样。
每个 entry 的 size 是一样的，都是64byte，它的资讯都是一个 virtual address 对到哪一个 physical address，然后再加它一些辅助用的资讯这样子。因为你一个 user process， 你可能有例如4GB 的资料要管理，那你4GB除以4KB 下来，你有100万个资料要管理，所以你一个 entry 是管理一笔资料，所以你会需要有100万个 entry。
OK，
那你100万个 entry， 你每个 entry 就会需要有一组对应关系，因为你一笔资料它都是拿到 virtual address 而已。对。
请教一下，这边也写到，
嗯，
多个公办员嘛，
对，
那你他马的话，应该很好理解，他应该有一个时间适应的部分，应该有。
对，
那 GPIO 也有可能也会提供这个部分嘛。那 UART 它是好像一个序列。
对。
那它这个会有可以作为终端的一个功能。
可以啊，它只要可以发讯号出来，它就可以让你。
但是它是在一个它 UART 就是一个有可能在一个城市里面，一直在那可能一直在监听它的东西。
对，那它可能就是
它的讯号，
它可能会周期性的发讯号给控制器。
所以说一般就是譬如说我直接在写程式的话，或是这样子，那你就是以那个什么那个什么Visual Studio 的话，假设我是写这个东西，我要跨越这个处理器的话，它会有一种类似的一个作用，
跨越处理器，
跨越的机制，就是说，我这个做跟另外一个做，我不允许他这样子去做。那假设，因为以前我也写过，就是说你连到我的网络，手机连到网络，我就把你关掉，
对
，shut down，
对。
但是这是在整个 IoT 里面，那时候是无意间他们没有锁住，我发现到那个 Visual Studio 那在2019版的时候发现到 IoT 的这个功能，但是我们现在好像 Microsoft 会把它拿掉，所以说你要用这个，譬如说它 URL，这可以，那我网络也可以，
网络也可以啊，网络的网卡也可以。
可是我也不可能就连到你，我们两个虽然有互通，但是我就直接我下达下达指令。
这里其实没有讲一件事情，就是你插入之后，其实它会需要有注册的动作。你这些 UART 或者是这些 GPIO，它其实都需要跟你的 control 做注册。那你在你自己电脑上本来它的就是硬体的型号本来就是可以直接注册，可是你从外部直接插进来的话，那就要看它的注册验证有没有过。对，所以它基本上它的 control 应该会有一个验证的过程，确保你是不是外部的装置进来有没有被认可这样子。对。那这边讲的 control 其实都是很基本，就是一颗 control，但现在的系统其实都不是只有一颗而已，就是其实现在系统都会有阶层式，它其实会有好几颗 control 在那边，去做，所以它是层层的去做验证，这个东西。
对，你说 SSH 我可以理解，那如果是说像这个好像就感觉
没有，SSH 是网络的这个连线。
对，
但是我刚才讲的是硬体的，就是你这个网络，你如果要把两个电脑用网络对接的话，你用一条网络线把它对接，这种才会有牵扯到 interrupt。
对了，我是说像 SSH，我直接不管是这样，我只要网络能通，我就可以下 terminal 下去的一些的 control 的指令嘛。
对。
那因为我感觉好像是这个序列簿这个东西啊，不管是 Scheller 或者是 I2C 啊，或者这样子等等，它在这整个里面写的时候，都好像有一道墙，似乎我们现在目前我们是很难突破 有些的东西是当然是在整个设计里面可能是可以，有些的部分像它这个序列部这些东西，好像就会有一道墙的感觉。对，没有了，我只是觉得这个序列部的东西好像有点怪怪的这样子，不知道是正确还是对。应该是大体上，如果是说我们现在如果说，
这感觉还蛮看它的实作，因为对啊，每一间公司的实作也都会不一样。
对了，如果是说我们答案是这个是对的，它也是一个控制源，就对了，中断的控制源。
概念上来讲是没错的。好，对，是这样。All right, so let's come back to push our progress. So we talk about there are best bit, worst bit, and first bit, right? But actually, Linux is not using those because those are all more the concept. They're all conceptual for implementation. So what Linux is using is about the very basic allocation is called allocate patch functions. So it allocates a single patch or two to the older patches, okay, and returns a pointer to the first patches patch structures like that. So this is the general allocations for I mean also the general hierarchy for how Linux manage this kind of allocator stuff. So for Linux, actually, because there is a user process and kernel, so we will first split to user space memory allocation and kernel space memory allocation. Okay, and the allocate patch label is a little bit above the physical DRAM, just like we are going to partition a physical DRAM to the patch frame, right? So after doing the partition to the patch frame, the low level memory allocator or allocate patch is going to manage all these kind of patch frame. So actually, we say there is a zone dash no more things for a kernel, right? And actually, zone dash no more, they can also, I mean, for the user, for the user process part memory, they are also called the zone dash no more. So actually, the zone dash no more is super large. I mean, that includes those for kernel and also includes those for the user. It just depends from the privilege. Okay. So from this body system or the low-level memory allocator part, it is in the patch granularity. So for kernel space memory allocation, it is a little bit complex because there are two ways. One is called a small size allocation. And for a small size allocation, if you are writing the kernel programming, then you will use a thing called the kernel memory allocator, okay, malloc. So for this case, it will be interactive with the slab layer. Okay, so this part is because when you are going to write the kernel code, there are a lot of kernel data structure. And kernel data structure usually is not as large as 4 kilobytes. Usually it's way more smaller. So how to manage those kind of small data structure stuff, then you will use this data structure stuff. But there are also some possibility as when you are writing the kernel function, kernel stuff, then you are going to maybe dynamically allocate a super large kernel buffer. So you also need the slice maybe larger than 4 kilobytes. So you will use another code, the virtual memory allocation stuff. And in this case, you can get a larger space from the DRAM frame, the DRAM patch frames. Okay, so for user memory allocation, actually, when you are using the memory allocation from C library, then there are two different ways to get the patch frames. The first is called BRK. The other is called the mmap. So it depends on the size. So mmap usually is for the larger size, and BRK usually you'll get one patch each time. Okay. So we'll first talk about this, the lower level part, just like what is the decision behind getting this kind of patch frame. Okay. So the allocate patch functions allocates a single patch or two to older contiguous physical patch. And the key thing is contiguous physical patch. Okay, and this whole design is called body systems. So body system will maintain things like less kind of data structures. So there are different kind of label here. So I'll just give you a quick example to better understand how body system work. So if a process requests 4 blocks, we say 2 to 2, 4 blocks. So 4 blocks is 16 kilobyte because one block is 4 kilobyte. But there is no free patch in order 2 and order 3. So this is the order 0, 1, 2, 3. So the idea is if now you are going to get for example, only one block, for example. So one block is you're going to get one patch. So if the body system checks the order, and if order 0 there is a patch, then we will directly do the allocation. But if there's not, then we will do the body system allocation. So in this case, if we have our request is 4 blocks, and we say like actually there is no free patch in order 2 and order 3, okay, so the body system will move to order 4. So the order is each time how large the system will allocate the memory. So for order 4, the system will directly allocate 2 to the 4 block. Okay, so 2 to the 4 block is quite just like 16 pages. So it is like 64 kilobyte. So the larger order, it means like the allocate patch function will directly allocate a contiguous a large memory. But it always starts from the smallest one to check about if there is free patches. Okay, so come back to our example. Actually, what we need is 2 to the 2 blocks. So the allocate patch will first check 2, but if there is no free patch in order 2, then it will check 3. And if in our case, if there is also no patch in order 3, then we will check order 4. Okay, and after checking the order 4, like if there is a patch, say 2 to the 4 block, we'll split this 2 to the 4 block to half, and then move to 2 to the 3 blocks. Okay, so if there are in this case, actually 2 to the 3 block, we will keep 1, and another 2 to the 3 will move to the 2 to the 2, right? So each time we will only keep 1 portion, and the rest of the portion we will move to the bottom layer. So in this case, 2 to the 4, they will we can split into 2 to the 3. So 2 to the 3 will keep 1 portion. So next time, if the request is like maybe in order 3, then we can directly return this. Okay, and the rest of the half, like 2 to the 3, will push to order 2. So order 2, we will do the same thing. We will split into 2 to the 2. So one is here, and then the other one, because our request is 2 to the 2, so the body system will directly return the 2 to the 2 to the request. And now, after serving the request, actually now the body system for order 2 and order 3, they are one block. So for this, for order 2, we have this. Order 3, we have this. Okay, so next time, if you have another request is, hey, I'm going to get the 2 to the 3 blocks, let's say, add patches, then order 3 will directly return. Okay, so if you use up all this kind of portion, then allocate patches will ask for the higher order. Okay, so I mean the maximum order here is like 10. So like 2 to the 10 is 1024 patches. So 1024 patches is like 4 megabyte area. Okay, so this is called a body system. Okay, but we say actually this is for larger requests, right? But if we are going to store data structure usually is smaller than 4 kilobytes. So body system cannot help that much. Then how should the kernel do? Okay, so there's a thing called slab layer. Slab layer is about grouping kernel objects into slab cache, pre-allocating memory patches in slabs, and it can lead to the faster memory allocation. So slab layer actually in Linux, usually people also call them the data structure cache. So it is mainly designed for the data structure. So when the data structure is no longer needed, it is returned to the free list instead of deallocated. Because when we are using a slab, then if you are going to free the data structures for one process, then probably the other process later, maybe you will need the same data structure. So we don't really need to do the allocation at that moment. We can keep the data structure. We just don't destroy it. We just don't delete it. And maybe several hours or a day later, there is a new process and the process is going to use this data structure, then we don't really need to allocate a new memory space for the next process. Okay. So here comes an example, like there are process descriptor, right? So it is a free list of text structures. And there is also file object. File object is called inode, and there is also the semaphore. So what do I mean? Like this. Here comes the data structure as text structure. This is the very beginning we know about the Linux data structure. And process descriptor, this probably, I'm not quite sure, but let's say, assume this is like 100 byte. Okay. So the second text structure is another 100 byte, and this is another 100 byte. So now you say you have the process one only in this text structure. Process one is maybe is destroyed. We are going to delete process one. Then after terminating process one, we will not directly remove this text structure. Why? Because maybe later there is a thing called maybe process n. Process n is new created, and process n also need this text structure, right? But at that moment, if there is a text structure now in some memory area, then we can directly reuse this text structures. We just need to refill the data in this all this kind of field. We just need to change those kind of field from like process one's value to process n's value. So for this use case, we don't really need to reallocate a new memory area for other process. So this is quite important concept, because if we do the allocation too frequent, then there will be a lot of inner fragmentation, right? Because those kind of structure, they are smaller than 4 kilobytes. So you do the allocation so frequent, then there will be a lot of hole, and then you need extra time to do this kind of body system and step management. So the same things. This is the semaphore. So this is the semaphore data structure. Actually, there are all these kind of field. So for example, if this field is, let's say like each of them is 4 byte, then here comes like around 10 fields. So this probably is around like 40 something bytes. It is way more than 4 kilobyte, right? So for this kind of data structure, okay, if we directly allocate a new one for each of the new semaphore, then you will eat up a lot of space and you will be a lot of fragmentation. But the key idea is if we have SLAB there, then we can reuse those outdated semaphore for the new semaphore. We don't really need to allocate the new memory for the new semaphore. We just reuse those already existing semaphore data structures in the systems. Okay, so we can save a lot of time, and we can set the time to do the defragmentation. So the same things, this is the inode. So inode is so large, like there are way more fields here. So inode is going to manage the file stuff. Okay, so there are a lot of fields here. So probably this inode getting a larger capacity is needed, right? Okay, and we say we are going to reuse the data structure, but the thing is, if we mix all these kind of data structure together without a good management, then there will be a lot of inner fragmentation. So one very important idea behind SLAB there is we need to differentiate each data structure. So for this area, for the text structure, it should be isolated. We cannot allocate it for other data structure. So for the memory cache frames, we cannot share between inode and semaphore because inode is so large. So each data structure should have their SLAB cache. Okay, so this is the key things behind SLAB there. So SLAB there acts as a generic data structure cache in there. Oh, okay, so if frequently used data structure tend to be allocated and free open, so we just cache them. We don't really destroy, we don't really deallocate them. Because frequent allocation and deallocation can result in memory fragmentation, and also your kernel needs to do a lot of stuff. So you will pay off a lot of kernel performance to do this kind of stuff. And this SLAB there, or like the SLAB stuff, can be made per processor. So no locks are required for allocation and deallocation. Okay, and it can be NUMA aware also. Okay, So the key idea is to avoid from allocating and freeing physical address as frequent as possible when there's new requests for creating a new data structures. So the structure is like less. So slab is using the things called cache. So the structure is cache, slab, and patch. So this patch is called like patch frames. Okay. So cache is one cache per object. So text structure has the text structure cache. INO has an INO cache. Semaphore has a semaphore cache. So different data structure, they have their own step cache. So below the cache, actually there are called slabs. So like less. So one slab usually it is a contiguous memory. So like maybe probably there are one or two pages. It depends. So in this example, if one slab is like 2 pages, then the 2 pages we will only store the text structure inside this slab area. Because for example, if this slab 1 is belonging to the text structure cache, okay, so you can see there are only text structure inside. We cannot store INO inside. We cannot store the semaphore inside because they are different data structures. So they are belonging to different data structure cache. Okay. And now if the slab 1 now they are all, for example, there are 4 processes and each process they already store their text structure in slab 1. Okay, then we will open up another step called step 2. Okay, so for step 2, there is a probability is called unpartial list. Unpartial list is maybe some text structure they are unused. The reason for unused probably is maybe there are some processes they are terminated. So after processes are terminated, those text structure will become unused. They are not belonging to any process. Okay. And there is another status for slab is called the free. Okay, so free is called, empty. Empty is all the text structures inside the slab that they are unused. Maybe all the processes they are deallocated. Okay, so for each cache there are 3 different status. So each status they have only their own slabs. So there are a lot of slabs for slab flow. There are a lot of slabs for slab partials. There are a lot of slabs for slabs free. Okay. Okay. So we run how to run the allocations. So we only when there does not exist any partial or empty slabs in each cache, we will run the allocation. So that means if, for example, if there are partial or empty list, there are those kind of unused text structure area, we will directly reuse them. So for example, if there is a new process called process N, and process N has their text structure N, it will directly use this area. So in this case, we don't really need to allocate a new patch frame for the new process. What we are going to do is we directly assign this memory address for the new process, and then the new process can put those process-related information in this memory patch frames. So when will we run free? So free is only when available memory grows low. Like free is, if we are going to free this data structure, there's one possibility is if DRAM doesn't have enough space, right? We need to reclaim the DRAM. So we will first reclaim this empty space. So like maybe other process or like other allocator can get more kind of space. Okay, so this is how we're going to run free. Okay, so this is slab layers. Okay, so here comes 2 common libraries to allocate kernel memory. So one is the right-hand side part is for small slice, and kernel memory allocation we already introduced. It is based on a slab layer. So for this kernel memory allocations, you will interact with the slab layer. So usually this path they are all designed for the data structures usage. And the left-hand side is usually not for data structure. It's usually for your stack or like your dynamic memory for the kernel. So we do a very quick comparison between this kernel memory allocation and like virtual memory allocation for kernel. Okay, so the kmalloc functions obtains kernel memory in bite-sized chunks. So the reason like it can do this kind of stuff is because like this. For each patch, inside each patch, we still can do the management. Like this text structure probably is smaller than patch. So we can do a more finer granularity management. Okay, so this is all because we have step there. Okay, so memory allocation, just a notice, like memory allocation is in C library. So this is not the same here. I mean, those vmalloc and kmalloc, they are all for the kernel programmer. So when you are writing the kernel, you are going to do the kernel development, you will use those kernel functions. Okay, and C libraries, memory allocation, those are all for user process, user applications. So they are totally different stuff. Okay, so if we need a whole 4 kilobyte patch, then this K memory allocation will request for the allocate patch in prior slice bit better. So like this. So if we are going to get the 4 kilobyte, usually we will directly get from this memory allocation, and we can get a 4 kilobyte from here. So this is what we say larger page size is, larger data size is the best is about if it is larger than 4 kilobyte or if it is smaller than 4 kilobyte. So this size, I would say it is 4 kilobyte. Okay. So with using this kernel memory allocations, it returns a pointer points to a block of memory that is at least the requested size. Okay. The v memory allocation function allocates memory that is only virtually contiguous. Okay, because if we are going to get 2 pages, 3 pages, 2 page frames, 3 page frames, then probably maybe it is not possible to get a contiguous 2 or 3 page frames. So when you are using the virtual memory allocation, it cannot always for sure you can get a contiguous. So you can only get a virtually contiguous one. That means your physical page frames usually is not contiguous. Okay. So because your physical is not contiguous, but the only contiguous stuff is the virtual part. So it requires patch table to maintain the mapping between the virtual and physical address. So for this part, even for kernel, you still need a patch table to do the mapping. Okay. So for this virtual memory allocation, actually, people now, system now usually use the on-demand way. So usually if you do the v memory allocation and then you when your kernel function really touches the physical memory, really touch this virtual memory area, then the patch frame will be allocated at that time. So it's not at the time you call a virtual memory function. It's the time when your code really touch the memory. In this way, it doesn't waste up too much of the memory, because maybe when you are doing a kernel developing, then you just miss allocating a super large memory area, but you don't really use that much. Then you will eat up a lot of memory space. So in kernel, actually, you use on-demand to allocate the physical memory for this virtual memory allocation. Okay, so regarding of performance, most of the memory allocation inside kernel usually use a kmalloc. The reason for kmalloc is because this is for using this kmalloc. Actually, in most cases, you don't really need to use a patch table to do the translations. And I will show you later, because this is a one-to-one mapping. Because kernel, usually you only get the limited amount of the memory. So using this kmalloc, actually it is, you can do the one-to-one mapping directly. So you don't really need to do a patch table translation. So you will be faster than including user process or those kernel functions using this vmalloc. So if system can get enough contiguous physical address all the time, then there nearly no address translation overhead as required, right? Because if you always can get a contiguous physical address, what you are going to do is just let your virtual address to add an offset, then you can get the physical. So the reason we need patch table is because your physical memory doesn't have enough space. Your virtual address space can be so large because virtual is a stuff like share between all the process. So each process you have like 4 GB of the virtual address space. Then assuming you have like 100 process or like 1,000 process, then what you need about the total virtual address space will be 4 TB or even 4 PB, right? Because each process maximum you can get 4 GB. So there will be a lot. But usually your physical memory doesn't have that much. Usually your physical memory is static, like you only have like 64 GB or 16 GB of your memory. So because this reason, there is the need for patch table translation. There is a need for the translation between virtual and physical address. So if one day your memory is super huge, you have zettabyte of the memory. So in this way, you don't really need to worry about your user process. I mean, all the user process have no enough memory, then we don't really need patch table actually. You can just do the direct mapping, then they will be super fast because you don't really need to do any translation. You get one virtual address and you just add an offset, then you can get the physical address. So for all the instructions, CPU run can be super fast. And you also don't need your TOP because you don't really need to record any translation result. What you only need is to know the offset. Okay. So virtual memory allocation is used only when the system requires large regions of like memory. Okay, because we have some time, so let's talk about some very also like this is a little bit complex, but I think this is quite important for you guys to understand about the kernel memory. So let's use 32-bit system as an example because 64-bit is quite different from this case, but the concept is the same. So we say on 32-bit system because we can only address up to 4 GB of the physical address space, right? So kernel only has 1 GB virtual memory, and what if system have 8 GB of the memory space? Then how to do this kind of stuff? So to address more than 1 GB, and the reason why kernel needs to have address more than 1 GB is maybe like if you are going to have some dynamic memory allocation in kernel, then probably you will need the memory patch frame more than 1 GB, and you can use the dynamic mapping there. So the solution is kernel address space reserve a 128 MB dynamic mapping area called a high memory. Okay, so high memory is memory that is not permanently mapped into the kernel's address space. So the thing like we say it is not permanent is you need a patch table. Okay, because if this is permanently mapped, then probably you don't really need the patch table. You can just like the k-memory allocation. So I think this is not easy to understand. So here comes some figures. So given there is a virtual address space on the left-hand side and a physical address space on the right-hand side. So now we say the kernel virtual address space is 1 GB. So here are zone DMA from 3 GB to 3.16 GB because DMA, if I remember correctly, is 60 MB only. Then from zone DMA to 69 GB, they are all for the zone normal. So zone normal, usually we use the k-memory allocation to do the memory allocation, right? Because in this area, usually it's about kernel data structures. So we need to integrate with the step there. We can get better performance. Okay, but the case is 3.869 to 4 GB. There are 128 MB. It is called the zone high memory. So this part, usually we can use the virtual memory allocation. So why I just periodically mention about kernel has a super fast translation is these are static. So usually in the physical address space, it is possible to directly allocate this at 96 MB area, right? Because if you still remember, no matter which user process, their top 3 GB to 4 GB, they are all for kernel. So all different user process, their first 1 GB will map to the same area as this area. Okay, so there's no problem to do this kind of static mapping, or we call it direct mapping. So direct mapping is how to get a physical address. Use your virtual address to plus and offset. Okay, because this is 3 GB and this is at 96 MB. So you need to add some offset to translate from this to this. Okay, but actually for this case, you don't really need the hash table because it's just about adding an offset. You just need to know the offset and you can directly translate all the entries inside this region. So this will be super fast. Okay, but the thing is, you still have this much of the physical memory. So if the kernel want to access those kind of data in this like region, then what we are needed is here. We need this kind of dynamic mapping to dynamic mapping the data from this area. But this is dynamic mapping, so actually we need a patch table. Okay, the patch table will help to do the translation from this area to any. So actually, because this is the virtual memory allocation part, so here is the possibility is if you have another user process, they can use their first 128 MB region can also be mapped to this region. Okay, so if you have more process, actually the total zone high memory will be huge. So this is the usage of like zone high memory at that time, because at that time, people are using 32-bit CPU. You only have 1 GB of the kernel, but now you now have 64-bit systems. So your kernel usually can have, if I remember correctly, it's 256 GB of the memory. So you don't really need this kind of high memory because you will never use up all the memory space. 256 GB is quite large. So actually in current 64-bit systems, this high memory is not really useful now. Okay, so maybe you will ask about, so when will we use this kind of stuff? So there are several cases like file caching, DMA, and network buffers. Those kind of stuff, we can use the high memory. Okay, one thing is, why here are DMA and why here is DMA? So zone-DMA is because at before a certain kernel version time, actually at that time, your CPU can only recognize a static number of the memory capacity. So your DMA can only put the data from DMA buffer to a certain fixed memory address. Okay, but after some time later, actually DMA can put the data to any place. But because Linux kernel is about, it needs to adapt to the prior version. So actually this zone DMA doesn't be removed. It's still there. Okay, but it is not used now for this usage. Usually zone-DMA, the usage now is just like zone-normal in current system, because actually your CPU and your controller now is stronger. You can handle more things, so you don't have this kind of limiting now. So zone-DMA in current systems, in current Linux system, is not function as we teach in this class. It is more like the zone-normal now. Okay, so high memory is a hack because at that time, like we don't have the 64-bit systems. So we need a kind of a trick to access the dynamic memory area to get more memory for if we have more user process, and each user process, they are going to launch different kernel functions. And then if different kernel functions, they need to have this kind of file caching area, then actually this will be a way to extend the kernel address, the kernel memory space. Okay. So this is about high memory. Okay, so let's move on to the virtual address space. And people usually call the virtual address space called the process address space. So for the virtual address space on Linux, each process is given a unique and flat 32-bit or 64-bit address space. So what do I mean unique? Unique is process can have different data at the same address in their own address space. So unique is actually for each programmer, when you are going to program a process, what you only need to know is you get a like 4 GB area, and you always start from 0, and the maximum is always 4 GB. No matter you are programming your first process, a second process, or even other programmers, they see the same things. Even they are seeing the same things, but when you put the data, for example, all the process, if they store the data in the first address, operating system will help you to avoid the contention. So this is about why virtual address space can be the unique. And a flat is about the modern Linux system does not use like segmentation stuff. So it is flat. Okay. So memory address is a particular value identify a specific byte in a process address space. So 32-bit address space means there are 2 to the 32 like bytes, and there are less amount of, this is 4 GB. Okay. So once again, we talk about kernel virtual address space. Here are temporary memory, just like the high memory, and then there are your kernel code, your data process, specific data structures, patch table, kernel stack, those kind of memory structure, text structure, those kind of stuff, they are all here. Okay, but how about the bottom 3 GB area? It is more like this. I think you are more familiar with this part. So this is for per process. So for each process, the top 1 GB is fixed, but the bottom 3 GB, it depends. I mean, the template is the same, but the content inside the template is different. So for example, the text structure is for your code. You have a process. So it means like you need a program, right? So your program usually is put in this text structure area. So because you have different process and you have different programs, so different program will be put in different like text structures. Okay, but the address is the same from a certain address number to a certain address number. And you have data sections and BSS sections, and they are all for initialized global variable or uninitialized global variable when you are running your C program or any program. And then you have user stack for each process. So it is going to store your kernel return functions stuff. Okay. And then here comes a heap. Okay. So heap is more like when you are coding this kind of memory allocation in your C library, right? So there's a heap structure. And then between them, there is a shared library. So shared library is like your C library, your standard IO library. So you can share between all those C program in your system. So because they are shared library, so actually they're here. Actually, this shared library will be directly mapped to the same patch frames. Then you can set your DRAM usage. So not every address is legal. So intervals of legal address are called memory area. So legal means actually there are permissions for different I would say dotted line box. So for this text structure, text section, probably it is executable like this. But for the data sections, maybe it is only readable, not executable. So different kind of box here that have different permission. So it will be belonging to different memory area. So because there are different memory areas, so once again, we need a things called memory descriptor to maintain the metadata for each memory area. So memory descriptor or structure, that structure, like if you go to check your Linux kernel, you will frequently see this data structure. So this is a kernel data structure, contains all information related to the process address space. So the memory descriptor associated with a given text is stored in this field of the text process descriptor. So this is, if you go back to the, I think it's lecture 1, when we're talking about the process descriptor, the text structure, actually there is one field, it's called MM. And this field is going to link to this data structures. Okay, so this data structure, there are several stuff here. So first of all, it's about mmap and like repository. So there are different ways, different data structure that contains the same things. So all the memory areas in the address space, they can be indexed by the linked list, or it can be also indexed by the wrap tree. So actually, like for this virtual memory area, there are several, for example, here. For the text structure, actually, you can think about like, probably there are several VMA, there are several patches inside here, because if your program is larger than 4 kilobytes, so there are a lot of, you can say, patches there. So if you are going to index where is the data, there are two different ways. One is using the linked list. So linked list is fast for traversing. And there's another thing is for wrap tree. So it is for searching. So this is two ways for indexing, but actually the content, the raw data, there's only one copy. There's not two. Okay. Okay. So there's another idea is about this, like, because each virtual memory area probably they can share between different process. The reason is now you process doing the creation, you use a copy on write, right? So if we have 2 process and 5 threads, so there are 2 different scenarios. We are going to do the differentiation. So MN users and MM account. MN users is about the address space users. So when we talk about the address space user, as for the MM users part is you have 2 process, and because 5 threads, because you will need to create threads from the process, right? So actually the address space, those 5 threads, for example, you will get, there is one process and create 5 threads. So the process and the 5 threads, they share the address space. Okay, and there is another process is having their own process. So the MM users now is the maximum is 6. Okay, so MM count is about the primary usage counter. So you have 2 processes and 5 threads. So the overall is like 7. So we will use this. Kernel will use this MM users and MM count stuff to decide about this memory area is shared between how many processes and how many threads. And when the process and threads, they are maybe free or they are created, and how to make this kind of identification. So going to the details, the memory area, or called VMA structures, describes a single memory area over a contiguous interval in a given virtual address space. Okay, so this is our MN structures, and I just zoom into several important stuff. Sorry. So this is the original MN structures, but now I only pick several fields related to the virtual memory area part. So this is quite small. Actually, there are 1, 2, 3, 4, 5. There are 5 fields related to this kind of virtual memory area stuff. So first of all, there is a things called like mmap stuff. So the mmap will be linked to this kind of VM area structures. So this pointer will point to these structures. So VM area, this is the first VM area, the second VM area, and the third VM area. So we are going to check about which VM area. So there is a start and next. Okay, so this VM area structures, actually, we can get this. I mean, this will be linked to this. Okay, and inside this VM area structure, there are a lot of VM virtual memory area. So why we need this kind of virtual memory area? That's because on our process virtual address space, probably they are belonging to different contiguous virtual memory. Okay, so those are all pages, and the contiguous virtual address we call one VMA. Okay. So now we are going to link back. So why we need those kind of contiguous virtual address? That's because we are going to map to this virtual address space. Because we say this text structure, this data section, this BSS sections, they all have their own privilege, right? So, for example, heap and BSS, there's no file path because those BSS and heap, there's only inside the main memory. And then, And then the data sections and the text sections, usually you have already the data in the storage device because you store your program in the storage device. So there is a file packet. Okay. I think maybe we can stop here and then we can resume next week. So thank you guys.
就是刚刚讲到是就是怎么样在跑的时候，然后成为那想知道是如果是在一开始，就是在初始阶段的时候，它会长什么样子？
就是
全部都是
这是最大的，它会有都挂最大的，然后从最大的去分下来，
就是列这个 memory， 然后这上分，然后是这里100
就是它会令到就是。对，它这边是资料结构，就是它这边会去说它的首个 virtual address 是多少，然后它多大这样子，首个 PCY 对多少，然后多大这样子，对，然后它就会把这一块把它移到下一层去，然后它就把它切一半，然后切一半之后呢，它就把后半段再往下层一步一步去摆这样子，对对对。
那另外问题是，它是你这个是那个 list， 然后刚才想为什么不是直接使用 kernel 里面的 list tag， 然后要
我觉得这个比较偏实作，就是它也可以用 list tag 实作，因为这个只是我截出来跟大家比较好理解，它是长这样子的，但是它实作 data structure 我并没有很按照 kernel 上面写，对，对 kernel 上面怎么实作要看它 kernel 怎么实作，对，但它是我觉得它高级可能是 list tag 没错，对，谢谢。
像这3种 step 有什么区别吗？
就是这边是满的，然后这边是半满，然后这边是全空的区域，就是对应到这边。如果你满的话，你这个 slab 就直接分配到这个区域，因为这样你就可以快速知道说，假设你要拿资料，你就会从这个 partial 这个区域拿，你这边拿出来的 step 一定都会有空间让你去放。
空间是指
就是它这个 slab 的话，你一个 page 里面都只能放固定的资料结构，就是你都只能放 text function。那你今天如果就是例如你今天 create 了一个新的 process， 因为你 create 新 process 你就会需要一个新的 text structure。那你这个新的 text structure 它如果可以直接从这边的 step 直接拿的话，你就不需要再去分配新的空间了。
拿了会变到这边吗？还是不会？
不会，那就这边它都变 use， 它才会变这边。它这边的变化是你这边全部都用完，它就会变成是，它就会把它移到这个 flow 来，flow 来。
所以是如果这个用了，这个用了，
对，
是整个才。
它整个用，然后你这个如果有用了一个之后，它就会从这个变到这边来。对，它就只是一个小管理啊，我觉得。对。
这地方，问一下为什么这边不直接用，就应该用 offset， 然后这边放一块，你这个
因为它不
给它就好了。因
为这里它是它是动态去分配的，所以你拿到的 physical 不会是连续的。你是在你开始在跑程式的时候，你开始去分配说啊，然后你可能程式跑10几分钟之后，你又说你不要那一块，所以它别的程式也会同时在用，所以你高几率是拿不到连续的记忆体位置。
对，这一块是因为我在 kernel 可以function 需要一些机体。
没错。
分配。
对，这块是系统都还没跑之前就已经先分配好，所以它一定是连续的。对，
不行，
谢。
我想问一下那个 process scheduler 的问题。先是这个就是 ONG 那边，就是它是就是当有多个 core 的时候，它也是就是其中某一个 core 执行那个就是 process 的时候，它会就是锁掉，然后其他 core 就是不能往里边加新的 process 是吗？
这样确认一下，
就是这张 PPT 就这个，就是不是说它
对，
有个
没错，
这个 round two 嘛，然后就是它是 multi core， 就当其中某一个 core 执行的时候，它会 lock， 然后其他别的 core 是没有办法 insert。
对，只要有一个 core 在就拿到里面的这个 这个 PID， 它就会整个锁住。对，
然后还有一个问题就是到 CFS，就是它是 dynamic 的原因是因为它的 delta execution 是动态的。
没错，因为它是根据你现在跑了多少，然后去换算的。然后它是根据痊愈的状况，因为你每个 process 可能都会跑一点，所以它是动态去调整这个 delta
因为不是有计算公式吗？所以是因为这个值是动态的，所以它是动态。就是这个 delta execute 它实际上是 CPU 的执行时间，但这个 vrange 就是相对于 OS 来说，操作系统来说的执行时间。
可以这样说，没错，可以这样说。
那但是我们以那个就是例子来讲，它 P1 是执行了0.1秒，然后 ms，然后那个是执行了0.05，但是他们俩加起来的总和就是没有到那个我们的一个周期6，所以就是在整个周期里，就每个 process 它其实不只会就是 context switch 一次，对吧？
对，
就是它可能会被
做
多次。
没错，就是越接近用完的时候，大家就会换的越频繁，通常
换的频繁。
对，因为他是希望让每个人都可以用到，所以他基本上会渐渐的把大家的都用完这样子。对。
所以其实我们计算出来的那个 allocated 的 CPU time 就是有什么用呢？因为我们在后面的计算里没有用到那个 allocated 的 CPU time，然后我们实际上计算，比如说我们分配给他的是5.9秒，就是这个，这个5.9秒不是 allocated CPU time，
对，
那它这个值我们算出来有什么用？
它不能用超过这个值。
它就是给了它一个 upper bound。
没错，它不能超过这个值。我觉得也不能说 upper bound，就是说它一定会用到这个值，只是有人会先用完，有人不会先用完这样子。就是这里的5.9是我举例来说好了，因为你 P1 在跑，你 P1 有比较高的，对，你 P1 有比较高的优先权，所以你在跑的时候，你可以很有可能你会先把这5.9就用完，这是有可能的。然后呢，你用完之后你就不能跑。
就是多种可能性，但是我们讲的是就是它要经过 I/O 这一种可能性，但也有可能它不用经过。
没错。
懂了。然后就是还有这个就是那个计算公式里面有个 nice 0weight，就是它是
作为基准去用的。
怎么选择？它是个固定的值吗？就是
它是固定值。
什么？就是
不是
P1、P2、P3，然后也是这个 nice 0。
没错，那是固定的。
固定的。
对，它就是去对标到 nice 0这个 weight。
它不是可选择，它是个常数量。
它是个常数。
好，就是好。
它的设计就是把那个当成标准这样子。
然后老师还有一个小问题，就之前讲的，可能我 KB 和 GB 没有分清楚。我们讲 page table 是 KB 还是单位是 KB 还是
GB？page table 到现在其实没有讲到 page table size 它其实是会浮动的，然后 page table size 其实很大。对，你想讲的应该是 page 吧？page 是4KB，就是一
frame 吗？
对，page frame 跟 page 有4KB。
但是 page table 不一定。
对，因为 page table 就是要看你在 user 在用的时候，他用了多少个 page， 那用一个 page 呢，它就会去就是有一个64 byte 的空间被用掉。对，但是你用了 page 很多的话，就是你可能动态是分配，你的 page size 都不会变，都是4KB，可你 page table 会一直涨，所以 page table 是可能很大的。但是 page table 多大这件事情呢，现在都还没有讲，因为最后面这个章节最后面会讲说 page table 要怎么去大概估算它到底有多大。对，
老师还有个问题就是这个微 runtime 就是它的公式和上面那个不太一样的。
上面那个是
对的，还是以上面这个为基准吗？以这个为基准吗？对吧？
我想一下哦。好，我这边应该漏改到，对，以这个，对。
就是我也想确定一下，就是这个 process context 它包含了 user 和 kernel 的两个状态下的 data struct。那然后 user 就对应的是这个 user address space kernel 就是 kernel，
对啊，都是对。
这三个都是储存空间，就是还有 hard register 这三个就是，所以 process context 描述的是这三种形态的储存空间吗？三种不同的。
我觉得它比较像是描述三种不同的资料，就是我储存空间嘛，因为它比较像是
都是 space 就是
我懂你的意思，但是因为因为毕竟一个 address space 里面含有很多种不同的资料，就例如这边说的 user address space 是这样子一个这么大的空间，然后它里面有各种不同的资料的形态，对，所以你要说空间嘛，也直接翻译过来是对的，但是它其实就是你可以讲它就是各种不同的 user 所需要user process 所需要资料的总和这样子，
就是这个 process 所需要的不同资料，
对，
那种。好，谢谢老师。
好，谢谢。
我们期中考试
就下一班
29号。
对。
我原本是这礼拜五要报备的，但我刚好那个期中考，我可不可以换到其他？
那你寄信给我好了，还是你有寄给我忘回？
我有寄给助教，但
助教，那你直接寄给我信箱好了。对，
我直接跟你说。
对，你直接跟我约。好，谢谢。
我可以问一下 body system。
白讲可以啊。
那个就是刚刚没有听懂它怎么运作。
它其实是一开始的时候，它会直接先分给 maximum order 最大块的，它一开始只会把机体切成最大的几块而已。然后呢，它就会开始有 recur 进来了。好，假设你今天 recur 进来是你想要你只有要一个就是一个 page 好了。一个 page 是2的隐次方，对吧？所以它只是0，那0里面没东西啊，因为空的，它就开始从最上面这个它其实会有很多块，因为你这个最大其实10嘛，2的14方其实只有1024个4KB 而已，所以就是4连 B，但你机体动不动就是 GB 等级，所以你这边其实会有非常多块，它就随便拿一块，然后也不是随便啊，就 FIFO 拿一块，然后呢先把它丢到下一层去，那下一层是2的9次方代表它是那个512，对吧？那512的话，其实就代表是512等于是1024除以2，所以你1024拿下来之后，你会有512加5122块，那你会保留一个512，把剩下的512个 page 的这个连续的空间丢到在下一层去，然后以此类推，它就会都保留一块，然后丢到下一层，这样子的话，一直到最下层，就是每一个人现在都有一块了，然后最下层有一块，那最下层那一块呢，就给你那个刚才要一个 page 的人，对，那你现在下一个人既然还有没有又没有了，他就再跟上层拿，这样以此类推，如果都没有的话，就再到这个 maximum order，再把拿一块大出来，然后再把它3分这样子。
那为什么要这样分？
它这样分可以确保比较对连续的。它可以比较容易确保它的分配的大小是连续的，因为你来的时候，你如果我举例来说好，你如果要的都不是4KB，你要的是这个4的话，那按照这个系统来讲，你可以很容易拿到4，那如果没有，就是再从上层去切而已，所以它是比较有系统方法去尽可能让 user 的需求是可以达到连续的效果。
我可以懂是。就如果我们随机选一个，然后拿出来给他用，那就会是随便乱。
那就没错。
那我们是从原本有使用这一区块，然后拿一部分给他用。
对。
这一使用这一区块会切很小，去给各个人去使用。
对，没错。
好，那这个架构在说什么？我刚刚没有听懂 A malloc 和 B malloc 差别。
这个架构在说，首先就是对于 Linux 来讲，它其实有2种不同的用户一种是不能说对 Linux 来讲，对系统来讲有不同的使用者，就是对这群 page firm 来讲，它有 user 的使用者，也有 kernel 的使用者。那 user 使用者只能透过这条路去做机体分配，那 kernel 使用者透过这条路去做机体分配。那 kernel 的使用者它比较复杂，因为 kernel 它的资料结构是蛮小的。就是 kernel 这件事情，我觉得也不能说比较复杂，应该说 kernel 比较可以被预测，所以它可以有比较多优化。 user 是没办法被预测，因为 user 就是你系统跑起来之后，你才开始要服务 user，所以没什么好预测的，它就是来人就要开始服务它。但 kernel 就是你本来就是 kernel 就是放在那边，你把它唤醒起来，然后你就把它安装来做使用。所以有什么资料结构，其实你本来就知道，对你还没跑之前就知道了。那这些资料结构其实都很小，所以你没办法把它真的都以4KB 来做管理。好，但是要怎么办？因为你现在 page 就分出来的4KB，一个比较简单的方法就是我让它同一个资料结构的人尽可能的集中在一个区域里面，集中在一个 page 里面。为什么要这样做呢？因为同一个资料结构的人代表它的大小是一样的，所以他去仿造了 page，他仿造了 page 的概念，因为 page 就是把所有人都切成一样大小。那你如果一个 kernel data structure， 假设像 text structure， 它假设是我随便讲好了40 byte 好了，那你所有人的 text structure 其实都是40 byte，因为它是固定的嘛，就是你一开始你在写 kernel 的 programming 的时候你就已经写好了，那你 process 越建越多，你 text structure 越来越多，那他们这群 text structure 就会全部被集中在几个 page 里面这样子。那它的好处就是它今天它可以做到更细的管理，因为原本来讲都是4KB 4KB 管，但你现在 text structure 是40 byte，所以你等于是可以做到40 byte 的管理。那你每次40 byte呢，其实你也不用把它丢掉，因为你的那个 process 其实在系统里面它是会一直被 create 出来的。那你也有很多 process 可能就死掉了。所以其实你可以让刚被建立的人，刚被建立的 process 出来，然后去使用这些死掉的人的死掉的 process 的资料结构。你就不需要去重新去 allocate，因为对于 memory allocation 来讲，最怕的事情就是你要非常频繁的去做 allocation，因为频繁做 allocation， 就算是 body system， 你也很容易就会遇到没什么好分配连续的。只要它分配不是连续的话，它就会需要有第一个就是它就一定要 page table，然后第二个就是它就会需要有额外的成本要去做回收，因为你现在当然你现在分配那个时间点不需要做回收，可是你 long term 来讲，你还是要需要把它回收回来。对，它就是基于这个概念，所以它设计了一个这个 K memory allocation 这条路。它这个 V memory allocation 我觉得就跟左边是比较像，它就是你总会有超过4KB 的需求，那就是你今天如果你的 kernel 想要把你的 page cache 再长大一点，你想要有更好的 cache buffer 的空间，那你就是会用这个去扩充。但是这件事情它无法在你跑之前就预测，因为你 kernel 你要就是多少资料去做 cache， 有可能是跟你的网卡给你多少资料 ，disk 给你多少资料有关系，所以它是跑了之后才知道的事情。那跑了之后才知道的事情，就没办法预先帮你把记忆体都先割好。所以它这个地方其实就跟 memory mapping 就很像，反正就是动态的割给你。因为动态的割，它就一定，不能说一定，但是它高几率就不可能给你连续的physical address。那只要它的 physical address 不是连续，那这一块它就需要靠 page table 去管理。对，大概这样。
然后刚刚提到这个，好奇，它这边有一部分
我就要关一下录音，我电脑还没电呢，等一下。